Question number 12 is about an elastic collision between a hydrogen atom and a stationary carbon atom. The hydrogen atom is travelling at 500 meters per second initially, and it makes a head-on collision with a stationary, so that means the velocity of the carbon atom initially is 0. So all of the momentum and the kinetic energy in the before picture is going to manifest itself in the velocity of the hydrogen atom. The collision is perfectly elastic. Now when I see that elastic, I'm thinking that energy kinetic is conserved. And that could make for an easier calculation under some circumstances. After the collision, the hydrogen atom bounces back. Now that's important, with a speed of, so this is actually going to be minus 420 meters seconds to the minus 1, because it's going in the other direction to this velocity, and velocity is a vector. Figure 1 shows the atoms before and after collision. The mass of the hydrogen atom, so this is in subscript H, should we say, is 1.7 times 10 to the minus 27 kilograms. That makes sense. And the mass of the carbon atom should be about 12 times that, and this is going to be mc, mass of the carbon atom. Calculate the velocity of the carbon atom after the collision. There are two approaches here. I'll do one, which is the conservation of kinetic energy, followed by the other. I think the conservation of kinetic energy is less likely to cause an error, but the conservation of momentum is likely to cause an error, so it's worth demonstrating both. So we're looking for the kinetic energy before the collision equals the total kinetic energy after the collision, because the collision is elastic. That means the kinetic energy before the collision would have been 1/2 times the mass of the hydrogen atom, 1.7 times 10 to the minus 27, times its velocity squared, 500 squared, closed brackets, equals. The total kinetic energy after the collision should be the same, and we know the kinetic energy of the hydrogen atom after the collision is going to be 1/2 times 1.7 times 10 to the minus 27 times by, and I will include it here, but you'll see that the negative sign is not necessarily needed here, so I'll put brackets minus 420 squared, and sort of you can see here why the minus sign won't cause problems in this situation when we're looking at energy, because energy is a scalar, close brackets, plus the mystery kinetic energy that we don't know, but we do know it's 1/2 times the mass of the carbon atom, 2.0 times 10 to the minus 26, times the velocity of the carbon atom that we don't know, squared, close brackets. So rearranging all this, stabbing it on the calculator, skip to the end, you end up with v squared equals about 6256. And v, the square root of that, there was one student who forgot to square root at the end, and that would give us about 79.1 meters seconds to the minus 1. So as all the numbers given to me in the question were to two significant figures, I'd write that answer here as 79. If we were to do conservation of momentum, then momentum P before equals momentum P after. The momentum before is going to be 1.7 times 10 to the minus 27 times 500 plus 500. That's the total momentum before, equals the total momentum afterwards. Now here's where I think the potential mistake might manifest itself. Mass times velocity for the hydrogen atom is going to be 1.7 times 10 to the minus 27 times, and I'm going to put this in brackets, minus 420. There you go. Plus the momentum of the carbon atom, 2.0 times 10 to the minus 26 times a velocity of a carbon atom that we don't know. If we were looking to do the conservation of momentum style, we should be expecting to produce exactly the same numbers over here. So we can rearrange this to make the velocity of the carbon atom the subject, and plug these numbers into our calculator. We've got 8.5 exp to the minus 25 plus, because of the negative velocity at the start of the question, 7.14 times 10 to the minus 25 equals, divide that by the mass of the carbon atom, 2 times 10 to the minus 26, and we end up with 78.2 meters seconds to the minus 1, which is pretty much the same as what we've put as our answer there.